Welcome to your Grade 9 Science Term 3 Final Explainer. Let's get you totally ready to crush this test. We're pulling directly from your official Al-Zaydiyah Boys Study Guide. No surprises here, just exactly what you need. Here's the game plan. 25 multiple-choice questions on Swift Assess, 120 minutes on the clock, and yep, calculators are allowed. We're tackling 4 core areas today: matter, fluid mechanics, classifying matter, and energy resources. All right, let's dive right in. First up, matter. You gotta compare states by volume, shape, particle spacing, and those invisible forces between them. Think of the kinetic molecular theory like a microscopic dance. Particles are constantly moving, completely changing how matter behaves. Watch out for heating and cooling curves. Remember those flat horizontal lines? That means a phase change is happening. Moving to fluids. To calculate pressure, just divide force by area. Always use pascals, or PA, as your unit. Why do massive ships float? Archimedes' principle shows us it's all about the upward buoyant force of displaced fluid. Squeeze a closed water bottle, and pressure increases everywhere inside. That, my friends, is Pascal's principle in action. Ever wonder how airplanes fly? Bernoulli's principle proves that faster-moving fluids actually create areas of lower pressure. Shifting to chemistry, remember, intensive properties ignore size, while extensive properties like mass completely depend on it. Can you see the different parts? If it's perfectly blended, it's homogeneous. If it's chunky, you've got a heterogeneous mixture. Look for obvious visual cues like color changes or bubbling. That means a chemical change created something entirely new. Never forget the golden law of conservation of mass. In absolutely any reaction, matter is never created or destroyed. Let's talk sustainability. Balancing our use of infinite renewable resources against finite, non-renewable ones is crucial for our planet. Fossil fuels don't just magically appear. They take millions of years of intense heat and pressure on organic matter. Because fossil fuels take so long, understanding how mechanical generators convert renewable energy into electricity is a real game changer. Finally, our growing population strains Earth's carrying capacity, making proactive conservation efforts absolutely essential for our survival. You've got this. We've totally conquered matter, fluids, chemistry, and energy. Now go put that awesome knowledge to work. So, are you ready to ace this exam? How will the science you master today shape our entire tomorrow? Welcome to your Grade 9 Science Term 3 Final Explainer. Let's get you totally ready to crush this test. We're pulling directly from your official Al-Zaydiyah Boys Study Guide. No surprises here, just exactly what you need. Here's the game plan. 25 multiple-choice questions on Swift Assess, 120 minutes on the clock, and yep, calculators are allowed. We're tackling 4 core areas today: matter, fluid mechanics, classifying matter, and energy resources. All right, let's dive right in. First up, matter. You gotta compare states by volume, shape, particle spacing, and those invisible forces between them. Think of the kinetic molecular theory like a microscopic dance. Particles are constantly moving, completely changing how matter behaves. Watch out for heating and cooling curves. Remember those flat horizontal lines? That means a phase change is happening. Moving to fluids. To calculate pressure, just divide force by area. Always use pascals, or PA, as your unit. Why do massive ships float? Archimedes' principle shows us it's all about the upward buoyant force of displaced fluid. Squeeze a closed water bottle, and pressure increases everywhere inside. That, my friends, is Pascal's principle in action. Ever wonder how airplanes fly? Bernoulli's principle proves that faster-moving fluids actually create areas of lower pressure. Shifting to chemistry, remember, intensive properties ignore size, while extensive properties like mass completely depend on it. Can you see the different parts? If it's perfectly blended, it's homogeneous. If it's chunky, you've got a heterogeneous mixture. Look for obvious visual cues like color changes or bubbling. That means a chemical change created something entirely new. Never forget the golden law of conservation of mass. In absolutely any reaction, matter is never created or destroyed. Let's talk sustainability. Balancing our use of infinite renewable resources against finite, non-renewable ones is crucial for our planet. Fossil fuels don't just magically appear. They take millions of years of intense heat and pressure on organic matter. Because fossil fuels take so long, understanding how mechanical generators convert renewable energy into electricity is a real game changer. Finally, our growing population strains Earth's carrying capacity, making proactive conservation efforts absolutely essential for our survival. You've got this. We've totally conquered matter, fluids, chemistry, and energy. Now go put that awesome knowledge to work. So, are you ready to ace this exam? How will the science you master today shape our entire tomorrow?
All right, let's jump right into it. Welcome to this explainer on matter and thermal energy, or مراجعة امتحان المادة والطاقة الحرارية. If you're gearing up for a big test, or honestly, if you just want to deeply lock in your understanding of the physical world, you are in exactly the right place. Today, we're going to treat this like a masterclass study session. We're taking it slow, going into the high-level details, and building your knowledge step by step. By the end of this review, you're going to be totally bulletproof on these concepts. So, get comfortable and let's conquer this together.
Here's our game plan. First up, foundations, or al-asasiyat. Second, states of matter, halat al-madda. After that, we're going to put ourselves to the test with 3 solid blocks of practice questions to make sure everything really sticks.
Section 1. Foundations. We are starting with the kinetic theory, or an-nadhariyat al-harakiyya.
At the very heart of everything we're doing today is the kinetic theory. Basically, it explains how particles in a gas behave, and it can actually describe particle behavior in other states of matter too, or tafasser kayf tatasarraf al-juzaymat. I really want to let that sink in for a second. This single theory, it's your master key. If you can wrap your head around how these tiny invisible particles act, you can predict exactly how a solid, a liquid, or a gas is going to behave out in the real world.
Okay, so to actually use the kinetic theory, we've got to accept 4 ground rules, or assumptions. Let's walk through them. Number 1, all matter is made up of tiny particles, jisaymat sakhira, literally everything around you. Number 2, these particles are in constant, random motion, tataharak bistimrar o bishakal ashwai. They never, ever stop. Number 3, because they're always zipping around, these particles collide with one another, al-jisaymat tatasadam. And number 4, which is absolutely crucial for your exam, very little energy is lost when they collide. La tafqud al-kathir min al-taqa.
Picture those particles bouncing around in every possible direction. When they undergo these elastic collisions, bouncing off each other with a pow, they just keep going. They retain their energy without just dropping dead to the floor. Their behavior is perfectly, mathematically predictable, based purely on those 4 assumptions we just went over.
Section 2. States of matter, or halat al-madda, categorizing the universe.
So how does particle movement dictate what a substance actually feels like? Well, in a solid, or sub, particles vibrate in fixed positions. Because they're locked in, solids have a fixed volume and shape, hajm wa shakl thabitain. In a liquid, sa'il, the particles have a little more freedom. They slide past one another. Because they glide like this, a liquid keeps a fixed volume but flows to take the shape of its container. And finally, gas, ghaz. These particles move super fast and spread out entirely. Thanks to that absolute freedom, a gas takes both the shape and the volume of whatever container you trap it in.
But wait, there's a wild card here. We've got a 4th state to talk about, plasma, or plasma. This is a state of matter where electrons are actually stripped right away, forming an ionized gas. You only really find plasma at unimaginably high temperatures, like inside the sun or in a blinding bolt of lightning. And definitely keep this trivia in your back pocket. Surprisingly, plasma is actually the most common state of matter in the entire universe. Moving into Section 3, practice questions 1 through 4. Let's test our knowledge.
Question 1 asks, according to the kinetic theory, how do particles and matter move? Think back to our 4 assumptions. The right answer has to be B, constantly and randomly, or bishakl mustamir wa ashwai. They don't move in perfectly straight train tracks, they don't only move when you heat them up, and they for sure don't stand still. Constant random motion is the golden rule.
Let's apply that right into question 2. What happens to the energy of particles when they collide with one another according to the kinetic theory? If you recall those elastic collisions we talked about, you'll know exactly which one this is. The answer is C. They do not lose much energy, or la yafquduna al-kathir min al-taqa. A crash just changes their direction. It doesn't drain their battery.
Okay, question 3. Which state of matter is described as having a fixed volume but not a fixed shape? Let's consult our mental checklist. A solid? Fixed both. A gas? Fixed neither. It's the one that flows to take the shape of the cup you pour it into but keeps its exact volume. That means the correct choice is B, liquid or sail.
Section 4. Practice questions 5 through 8. Time to dig a little deeper.
Question 4 asks, what is the most common state of matter in the universe? See, I told you to keep that tip in your back pocket. Even though solids, liquids, and gases are everywhere here on Earth, if we zoom out to the stars in the sheer vastness of space, the answer is hands down D, plasma, or plasma.
Moving on to question 5. How do particles move within a solid state of matter? Think about how tightly packed a solid block is. Those particles do not have room to slide past each other, and they certainly don't fly around freely. The only way they can move is by shivering in place. So the answer is C. They only move by vibrating in fixed positions, or an ihtizaz faqat fi mawaqi thabita. Following up directly on that, question 6 asks, which of the following is responsible for a solid's fixed volume and fixed shape? Like, why are they locked in those vibrating positions? Well, it's definitely not high kinetic energy or rapid collisions. That's gas behavior. That rigid, unbreakable structure is held together by choice C, strong attractive forces holding the particles together. Quwwa tajadhub qawiyya.
Okay, stop right here. I need everyone to pause and listen closely, because we need to explicitly clarify a trap that catches literally so many students on exams. Thermal energy, takat al-harariya, and temperature, darajat al-harara. These are not the same thing. Thermal energy is the total energy, meaning both kinetic and potential energy combined of all the particles in a substance. Total. Temperature, on the flip side, is just the average kinetic energy of those particles. Average versus total. Keep those two strictly separated in your mind.
Let's test that logic on question 7. What is thermal energy? Based on the massive hint we just went over, we know we're looking for the word total, and it needs to include both types of energy. That leads us straight to choice B, the total energy, or ijmali taka, meaning kinetic and potential, of the particles. And right behind it, question 8 asks, temperature is a measure of which of the following? Again, temperature completely ignores the total, and it doesn't care about potential energy at all. It only measures the average speed, or kinetic energy. So choice A is the winner here, the average kinetic energy of particles, or mutawasit al-taqata al-harakiyya. Here we go. Section 5. Practice questions 9 through 11, the final challenge.
Question 9. Where does the potential energy of particles in a substance come from? We know kinetic energy is all about motion, but what about potential? Think about the invisible pull, almost like a stretched rubber band or a tiny spring between particles. The distance and that magnetic-like pull between them is exactly where potential energy hides, so C is our answer, the attractive forces, or quwwa al-tajadhub. Question 10 asks, which state of matter has particles with the highest energy that move freely to take both the shape and volume of its container? The magic word here is freely. Solids vibrate, liquids glide, but which one entirely fills up whatever room you put it in? That chaotic, high-energy freedom belongs 100% to choice C, gas, or gauze. And now, the grand finale. Question 11. A student compares two containers of the same gas. Container A and container B have the exact same temperature, but container B contains twice as many gas particles as container A. Which of the following statements correctly evaluates their energy properties? Let's unpack this piece by piece. The problem states they have the exact same temperature. As we just learned, same temperature means the exact same average kinetic energy per particle. But container B has double the amount of particles. Remember our strict definition of thermal energy. It's the total energy. If you have the exact same average, but you have twice as many particles adding to the pile, the total has to be higher in container B. Therefore, choice C is the only logical answer. Both containers have the same average kinetic energy per particle, but container B has a higher total thermal energy. Ijmali taka harariya ala. So the absolutely crucial takeaway we end on is this. Temperature isn't everything. The total mass, the sheer number of particles, matters just as much when calculating total energy. Which actually brings up a really fascinating thought to leave you with. If simply adding more particles increases total thermal energy without ever changing the temperature, how does this hidden mathematical reality affect how engineers design massive jet engines, or even how you efficiently heat your own home in the dead of winter? Think about that next time you look at a thermometer. Keep applying these kinetic rules to the world around you. Thanks for studying with this explainer, and good luck on your exam. Bit tawfiq fil imtihan. Hey everyone, and welcome to this explainer. Look, if you are gearing up for your physics exam on thermodynamics and the states of matter, take a deep breath. You are in exactly the right place. Today, we're going to break down these physical laws step by step using a really comprehensive bilingual review.
We'll be looking at these concepts in both English and Arabic to make sure you have absolute 100% clarity on the core principles. And honestly, more importantly, we're going to apply them to some of the trickiest questions you'll actually see on test day. I'll guide you through the visuals, decode the complex vocabulary, and make sure you walk in feeling totally confident.
All right, here is our study roadmap for today. First up, matter states, or halat al-mada. 2. Temperature, darajat harara. 3. Phase changes, tahayyurat al-hala. 4. We'll tackle question 12 head-on. And 5. Plasma questions, asilat al-plasma.
Section 1. Matter states. Halatul madda.
Okay, let's dive into this. This is our first core concept, the foundational rules of the physical universe when it comes to states of matter. I want you to anchor your attention right here on this incredibly helpful cycle. Notice the big purple arrow on the left pointing up? That represents adding energy, or ida fatata shika. When we add energy, we're actively driving processes like melting, vaporization, and sublimation. We're literally forcing matter to break its current bonds. Now look at the big blue arrow pointing down on the right. That's removing energy, izalat tashika. When we take energy away, we see freezing, condensation, and deposition. Over on the right side, you can actually see the cycle in action, moving from a solid block of ice to a liquid beaker of water, up into a gaseous cloud, and then right back around. Now, to make sure nothing gets lost in translation on your exam, let's briefly walk through this bilingual vocabulary table. Understanding these foundational terms is absolutely the key to unlocking the harder test questions later on. So we've got melting, al-insihar, where a solid becomes liquid by adding heat. Vaporization, al-tabahor, liquid to gas. Sublimation, al-tasami, where a solid completely skips the liquid phase and jumps straight to a gas. Then, moving in the other direction by losing heat, we have freezing, al-tajamud, condensation, al-takathuf, and finally deposition, al-tarsib, where gas turns directly back into a solid. Definitely keep these definitions in the back of your mind.
Section 2. Temperature. Darajatul harara.
So we know that adding or removing heat energy changes the state of matter, right? But what is actually happening on a microscopic level when we add or remove all that energy? Well, let's talk about temperature. If you memorize only one definition today, please make it this one. Temperature is a measurement of the average kinetic energy of the particles in a substance. Notice I didn't say how hot or cold something feels. In physics, temperature is strictly about motion. Kinetic energy means movement, so temperature is literally just a measurement of how fast, on average, the tiny particles inside a substance are zipping around.
Now, what's really interesting about this is how perfectly it visualizes that concept. Look at the top here. At high temperatures, the particles have those long motion lines behind them. They're moving faster. That's high average kinetic energy. Now look at the bottom. At low temperatures, the particles just have these tiny motion lines. They're moving a lot slower, meaning lower average kinetic energy. It really is that simple. High temp equals faster motion, low temp equals slower motion.
Section 3. Phase changes. تغيرات الحالة. Okay, now it's time to combine our knowledge of matter states and temperature to see how materials physically transform during phase changes. Let's start with the melting point, or nuktat al-insihar. This is the specific temperature at which a substance changes from a solid state to a liquid state. But here is a vital piece of information for your test. The melting point is the exact same temperature at which a liquid begins to freeze and become a solid. For water, 0 degrees Celsius is both the melting point of ice and the freezing point of liquid water. It's a two-way street that depends entirely on whether you are adding or removing energy.
And this brilliantly illustrates that concept. On top, we've got solid ice transforming into liquid water. On the bottom, liquid water freezing back into solid ice. But here's the catch. During this exact transition period, while the melting or freezing is actively happening, the temperature of the substance does not change. I know, it's a completely counterintuitive concept that trips up a lot of students. The thermometer stays completely still until the entire phase change is complete.
So you might be wondering, if we're constantly adding heat to melt ice, but the temperature isn't rising during the transition, where is all that heat energy going? Well, it goes into the heat of fusion, or hararat al-insihar. The energy is being used up entirely as hidden energy purely to overcome the attractive forces holding that crystalline solid structure together. It's busy breaking the bonds between particles rather than making the particles move faster. Therefore, the kinetic energy and the temperature stay completely flat during the melt.
And the exact same logic applies to vaporization. Liquids turn to gas at their boiling point. But it's actually fascinating to note how wildly different those boiling points are depending on the material.
At sea level, everyday water boils at 100 degrees Celsius, but liquid nitrogen? That boils at an incredibly cold -195.8 degrees Celsius. Regardless of the temperature, though, the heat of vaporization works just like the heat of fusion. During boiling, the added heat energy is used exclusively to break the liquid bonds to form a gas, so the temperature stays perfectly constant until it's fully vaporized.
Section 4, Question 12, السؤال 12.
All right, we've reviewed the theory. Let's shift gears into the application part of this explainer. It is time to get you ready to solve a tough, real-world exam question. Here is question 12. Read it carefully. When a substance transitions from a liquid state to a solid state at a constant temperature, what happens to the internal energy components of the particles? دعونا نفهم هذا معاً. Let's understand this together. Think about the rules we just learned regarding constant temperature and phase changes.
Let's look at our multiple choice options. Option A suggests kinetic energy decreases significantly. Option B suggests average kinetic energy stays the same, but potential energy changes. Option C suggests both increase, and Option D suggests particles lose all kinetic energy and stop moving entirely. I know these look super wordy and kind of tricky, but you already have the exact knowledge required to crack this.
So the crucial point is our definition of temperature. Step 1. The question states the temperature is constant. Step 2. We know temperature is the measure of average kinetic energy. If temperature doesn't change, the average kinetic energy absolutely must stay the same. That immediately eliminates options A, C, and D. Step 3. During a phase change, the energy being removed is changing the potential energy, allowing strong attractive forces to pull the particles into fixed, solid positions. Therefore, option B is the only logical, correct answer. See? When you know the definitions, the math basically does itself.
Section 5. Plasma questions. أسئلة البلازما.
Excellent work on that. Let's move to the next part and see how this builds as we transition to a lightning round of questions about the fourth and definitely most extreme state of matter, plasma. We'll walk through questions 13 and 15 together right here. Question 13 asks why ionized gas, or plasma, requires extremely high temperatures compared to normal gas. Look at option C. It requires massive thermal energy to allow electrons to be partially or completely stripped away. That is exactly what extreme heat does. It provides the sheer violence needed to tear atoms apart. And that leads right into question 15. What happens to atoms in plasma? Look at option B. Electrons are removed, or tisala el-elektronat. The atoms are literally ripped apart into distinct pieces.
Now let's knock out questions 16 and 17, which build perfectly on what we just learned. Question 16. What particles are found in plasma? Well, if we know that electrons are stripped away, we are left with negative electrons and positive ions. Therefore, the answer is A. Charged particles, جسيمات مشحونة. Question 17. What type of energy is needed to form plasma? As we saw with the massive thermal energy requirement, the answer is clearly D. Very high energy. Taka alia jiddan. To make absolutely sure this sticks in your memory for test day, let's summarize the anatomy of plasma as a simple, logical sequence. Step 1, you introduce very high energy. Step 2, this creates massive thermal energy that violently strips away electrons from their atoms. Step 3, the final result is a highly energized, ionized gas made entirely of free-roaming charged particles. From solid to liquid to gas to plasma, it's honestly all just a story of adding more and more energy. Which brings us to a final thought I want to leave you with today. How does the invisible energy we add or remove completely reshape the physical world around us? Think about it. We can't see heat, but we can watch it transform a solid block of ice into a charged, glowing plasma just by changing the kinetic energy of microscopic particles. Keep that incredible power of thermodynamics in mind as you review your notes. You understand the core concepts now. You know exactly how to decode the trick questions, and you are going to do fantastic on your exam. Thank you so much for learning with me today, and best of luck on your test.
Hey everyone, welcome to this exam review explainer. Look, if physical chemistry is giving you a bit of test anxiety right now, just take a deep breath. We've got this. Today, we're going to completely demystify phase changes and heat curves, going step by step in a really clear, guided session. Once we break down these patterns together, it's all going to click into place. So let's dive right in. Here's our roadmap for today. First, solids and phase changes. Then, the heat curve of water. Third, reversing that heat curve. And finally, thermal expansion and water. Okay, kicking things off with section 1, solids and phase changes. Because, we really need to understand how matter is structured before we can truly understand how it changes. So not all solids are created equal. Think about ice. It melts precisely at 0 degrees Celsius, right? But then think about stuff like butter or glass. These are what we call amorphous solids, or in Arabic, al-mawad al-salba ghayr al-mutabalira. Unlike ice, which has this really rigid, perfectly ordered crystal structure, amorphous solids just lack that strict internal arrangement. Because of that, they don't have one specific melting point. Instead, they kind of soften gradually over a whole range of temperatures. It's why when you leave butter on the kitchen counter, it gets perfectly spreadable way before it actually melts into a liquid. Now let's talk about some unusual phase changes and build up that vocabulary. Normally, matter goes from solid to liquid to gas, but sometimes it completely skips the middleman. Sublimation, or altisami, is when a solid skips the liquid phase entirely and turns directly into a gas. Dry ice is a really classic example of this. On the flip side, we have deposition, or al-tarsib. This is when a gas skips the liquid phase and turns directly into a solid. If you've ever woken up and seen those beautiful ice crystals forming on a freezing window, straight from the water vapor in the air, well, you've witnessed deposition in action. All right, let's actually apply these definitions to your test questions. Let's look at question 18. During which phase changes must a substance absorb energy? Well, think about it. To force a solid to melt into a liquid, or a liquid to vaporize into a gas, you have to add heat, right? You're literally forcing the particles apart. So melting, vaporization, and sublimation all absorb energy. That makes B our clear answer. For question 19, which is on deposition, going straight from gas to solid, the particles are actually losing their wild gas energy and aligning really tightly. That makes B the correct choice there too. And for question 20, why does the temperature stay perfectly constant at 0 degrees while ice melts? It's because all that added energy isn't actually heating the water. It's busy overcoming the attractive forces between the molecules just to break those solid bonds. So that's answer B. That energy we just talked about, the energy doing the heavy lifting of overcoming those solid bonds, actually has a specific name. It's the heat of fusion, or harat al-insihar. Simply put, it's the exact amount of energy required to change a crystalline solid into a liquid at its melting point. And keep in mind, the total amount of heat energy you need depends entirely on the mass of the substance you're trying to melt. Let's see how mass and energy play out in this next block of questions. For question 21, we have two containers, X and Y, and they're both at 50 degrees Celsius. So their average kinetic energy, their temperature, is exactly the same. But container Y has 500 grams of water, while X only has 100 grams. More water means more molecules holding on to heat. So even though they have the same average kinetic energy, container Y contains way more total heat energy. That's answer C. For question 22, the energy required to melt a crystalline solid is, just like we defined a minute ago, the heat of fusion, which is answer C. And question 23, solid iodine turning directly into a purple gas? Yep, that's our textbook definition of sublimation, answer B. Moving right along to section 2, the heat curve of water. This is where we actually visualize those phase changes. Let's break down the complete heating curve. We are tracking temperature on the vertical y-axis and time on the horizontal x-axis. Now, I want you to memorize the golden rule of this graph. Whenever the line is slanting upwards, the temperature is changing and the substance is in a single state, just solid, just liquid, or just gas. But when you see a flat horizontal plateau, that means the temperature is completely constant because a phase change is actively happening. All the energy is going into breaking bonds, not raising the temperature. Let's lock this framework into your memory. Region A is sloped, so it's just solid ice heating up. Region B is our very first plateau. It's melting, so solid and liquid coexist here. Region C slopes up, meaning it's just liquid water getting hotter. Region D is the second plateau. It's boiling, so liquid and gas exist together. And finally, Region E slopes up again, meaning it's entirely gas or water vapor getting superheated. The absolute crucial point here is knowing how to spot those dual states on the plateaus. So let's tackle question 24. Look at Region D. What phases are present? Well, Region D is that high, flat plateau at 100 degrees Celsius. Boiling is happening. Therefore, liquid water is turning into water vapor. Both liquid and gas are present, making D the answer. Now, question 25 asks about Region B. That's the lower flat plateau at 0 degrees. Melting is happening there, so solid ice and liquid water are simultaneously present. Boom, answer B. Now let's shift our focus to the sloped inclines for questions 26 and 27. Question 26 asks, which region represents water existing only as a gas with its temperature continuing to rise? Gas is obviously the hottest phase, which only happens after all the boiling is done. That's region E, making D the correct answer choice. Question 27 asks what's happening to the water molecules in region A. Since region A is below 0 degrees and slanting upwards, it exists entirely as solid ice, and its temperature is just increasing toward that melting point, so answer B is correct. All right, section 3, reversing the heat curve. Basically, we're going to read the exact same concept, but completely backwards. Instead of adding heat and moving from left to right, imagine we're cooling the substance down and moving right to left. Let's look at question 28. If we move backward across the plateau at region B, well, going forward, region B is melting, so going backward from liquid to solid has to be freezing. The answer is C. For question 29, what happens if we move backward across that higher plateau, region D? Going forward is vaporization, or boiling, so going backward from gas to liquid is condensation. Answer A. Honestly, to solve these complex multi-phase questions, we just use 4 sequential steps. Step 1, start hot in region E as vapor. Step 2, move left to region D, where we condense that gas into a liquid. Step 3, move down the slope of region C, cooling that liquid water. And step 4, hit the plateau at region B, where we freeze the liquid back into solid ice. It's like a roadmap. Let's use that exact step-by-step logic for question 30, starting top right in region E and removing energy until we reach region A. What's the sequence? Well, as we just mapped out, first we hit the plateau at D, which is condensation, then we travel down to plateau B, which is freezing, condensation, then freezing. That makes B our perfect answer. And for question 31, thinking about region C moving forward again, what phase is present? It's that middle slope. It is entirely liquid water, and its temperature is steadily rising toward 100 degrees. Answer C is locked in. And finally, section 4, thermal expansion. Here we'll look at water's totally unique behavior. It's amazing to think about how particle behavior affects our daily lives. When you heat up the air inside a hot air balloon, the particles move faster and spread apart, which causes the balloon to expand and rise. The exact same thing happens to concrete. In the intense summer heat, particles in the sidewalk spread out. That's actually why builders put those little seams or gaps in the pavement, so the concrete has room to expand without completely cracking. Even a thermometer works the same way. Heated liquid expands and rises up the glass tube. So here is our rule for thermal expansion, or al-tamaddud al-harari. When you heat a substance, its particles move faster. Because they're moving faster, they collide with more force and spread further apart. This spreading out causes the entire object to expand and get larger. Conversely, cooling slows the particles down, bringing them closer together, which causes the object to contract or shrink down. Let's wrap up with questions 32 and 33. Question 32 asks, what physical change takes place during thermal expansion? Well, based on our rule, an object expands and becomes larger due to an increase in temperature. That's answer B. But question 33, this one throws us a real curveball. What happens on a molecular level that causes water to expand as it freezes into ice? Wait, didn't we just say things contract when they cool? Yep, but water is a massive rule breaker. As it freezes, the particles rearrange themselves to line up their positive and negative areas, which actually creates empty spaces in the structure, making B the answer. And this brings us to what is perhaps the most important concept to take away today. Water is a highly unique exception. Above 4 degrees Celsius, water behaves totally normally. It contracts as it cools. But below 4 degrees, as it approaches freezing, the polar molecules start to arrange themselves into highly structured open rings. Because of these huge empty gaps inside the crystalline structure, water uniquely expands as it becomes ice. This expansion means ice takes up more volume but has the exact same mass, making ice less dense than liquid water. And that is exactly why ice floats. I really want to leave you with this final thought. We just learned that ice floating is a bizarre exception to the normal rules of physics. But what if water behaved normally? What if ice contracted, became denser, and actually sank? Well, during winter, lakes and oceans would freeze from the bottom up. Entire bodies of water would turn into solid blocks of ice, and literally every fish, plant, and aquatic organism would die. This single, tiny scientific anomaly, an empty space in a crystal structure, is quite literally what sustains life on our planet. Think about that as you walk into your exam. You've absolutely got this, focus learners. Good luck, and keep explaining the world around you.
Hey everyone, welcome to The Explainer. So glad you're here. Today, we're going to completely demystify fluid mechanics.
Seriously, if you've been feeling any test anxiety at all about forces, pressures, or those tricky hydraulic formulas, just take a deep breath. We're going to walk through these concepts step by step together, looking at the exact types of problems you'll face on the test. You've totally got this.
All right, here's our game plan for today. We're splitting this study session into 3 bite-sized sections. First up, buoyancy and Archimedes' principle. Then we'll tackle pressure. And finally, we'll master Pascal's principle. Step by step, we'll conquer them all.
Okay, let's jump right into section 1, buoyancy, or as it's called in Arabic, al-tafu.
So what exactly is buoyancy? Well, al-tafu, or buoyancy, is literally just that upward push a fluid gives to anything sitting partially or fully submerged in it. But how strong is that push? That is exactly where Archimedes' principle comes in. It tells us that the buoyant force on an object is perfectly equal to the weight of the fluid that the object pushes out of the way. Think about a massive steel ship. It floats because that big, hollow hull displaces a massive volume of water.
Now, whether something floats or sinks all comes down to a really simple tug of war. Picture a scale in your head. If the upward buoyant force is greater than or equal to the object's downward weight, boom, it floats. But if that upward push is weaker than the weight of the object pulling down, yep, it sinks. It really is that straightforward.
Let's test this out with a few practice questions. Looking at question 34, they're asking what the buoyant force equals according to Archimedes. Based on what we just talked about, it's exactly the weight of the displaced fluid. Then, for question 35, for a ship to float, its hollow shape just has to push enough water out of the way so that the upward buoyant force beats out its total weight. And question 36, this is a classic exam trick. You've got a light wood sphere and a really heavy lead sphere, both the exact same size, fully submerged underwater. Because their volumes are identical, they displace the exact same amount of fluid, so there is absolutely no difference in the buoyant force, or al-tafu, acting on them completely regardless of how heavy they are.
All right, moving on to question 50. Let's see how they try to complicate things. We've got an object experiencing a buoyant force of 15.88 newtons, and it's just starting to sink. The exam asks, what is the absolute minimum weight of this object? Let's hack this one together. Step 1, we already know the buoyant force is 15.88 newtons. Step 2, remember our rule? Things sink when their weight is strictly greater than the buoyant force. So for step 3, we find the tipping point, the exact moment. The absolute minimum weight, before it actually goes down, is when the weight perfectly matches that upward push. So the minimum weight for it to just begin sinking is exactly 15.88 newtons. Pretty simple when you break it down, right?
Awesome job so far. Now let's shift gears and move into section 2, pressure, known in Arabic as al-dakt.
So, pressure is basically a continuous physical force pushing against an object over a specific area. Check out this formula. P equals F divided by A, or pressure equals force over area. Honestly, I totally recommend memorizing this little magic triangle trick for your exam. You just cover up the thing you're trying to find. So if you need to find force, just cover the F, and boom, you can clearly see it's pressure multiplied by area.
Let's knock out a couple of quick foundational questions. Question 37 compares 100 grams of water to 500 grams of water, both sitting at 50 degrees Celsius. Now they have the exact same average kinetic energy because the temperature is identical, but that larger 500-gram container holds way more total heat energy, just because, well, there's literally more of it. And for question 38, what's the standard SI unit used to measure pressure? We're always going to use the Pascal, written as a capital P and lowercase a.
Moving on to question 39. A technician applies 50 pascals to a completely sealed container. So how much pressure is at the total opposite end? It's exactly 50 pascals. Why? Because pressure inside a closed container spreads out equally everywhere, no exceptions. Now let's take a dive for question 40. An underwater diver is feeling a massive force of 484,800 newtons spread over an area of 21.30 square meters. Using our trusty P equals F over A, we divide those giant numbers and get 22,760 pascals. To make that a little cleaner, just divide by 1,000 to convert to kilopascals, giving us 22.76.
Now, question 41 is pretty wild. Have you ever wondered how much force the actual atmosphere is pushing down on you right now? Standard atmospheric pressure is 101 kilopascals, which is 101,000 pascals. The average human has a surface area of about 1.6 square meters. Using our magic triangle, force equals pressure multiplied by area, so 101,000 times 1.6 equals a staggering 161,600 newtons of force constantly squeezing your body. Kind of crazy to think about. All right, question 42 is a super common trap, so pay attention here. We've got a child weighing 364 newtons sitting on a stool that weighs 41 newtons. The total area of the stool's legs touching the ground is 19.3 square centimeters. First thing we got to do, add those forces together. 364 plus 41 gives us a total downward force of 405 newtons. Next, and this is absolutely crucial, we have to convert those square centimeters into square meters by multiplying by 10 to the negative fourth power. That gives us 0.00193 square meters. Divide our 405 newtons by that tiny new area, and we get 2.10 times 10 to the fifth pascals.
And this sets up question 43 perfectly, because it brilliantly shows how this works in real life. That same kid leans back on the stool so only 2 legs are touching the floor. What happens to the math? Well, the total weight, the force, doesn't change at all, right? It's still 405 newtons. But the area making contact with the floor shrinks to just 2/3 of its original size. And remember, a smaller area means much higher pressure, or alduct. If we run the numbers with that new, smaller area, the pressure spikes up to 3.14 times 10 to the second kilopascals.
Question 46 is a really fantastic multi-step problem about a storm dropping the outside pressure by 15%. First up, calculate the area of the door. 1.95 meters tall by 0.91 meters wide gives us 1.7745 square meters. Now, a 15% drop in standard atmospheric pressure is roughly 15,198 pascals. When you multiply that pressure difference by the door's total area, you end up with a huge net force of almost 27,000 newtons pushing straight outward. Because the pressure outside suddenly dropped, the normal higher pressure inside the house actually forces the door out.
You guys are doing amazing. We're on the home stretch. Let's tackle our third and final section, Pascal's principle, known in Arabic as Mabda Pascal.
Okay, so this principle is basically the magic trick behind those massive hydraulic machines you see construction workers use. It says that pressure applied to a closed fluid transfers equally in every single direction. So the pressure at piston 1 is exactly the same as the pressure at piston 2. And since we know pressure is force over area, we get this really elegant equation, force input divided by area input equals force output divided by area output. To breeze through any hydraulic lift question on this exam, just follow this simple 3-step checklist. Step 1, identify your input forces and areas along with your output forces and areas. Step 2, plug them into that Fn over An ratio we just talked about. And step 3, just cross-multiply to solve for whatever variable is missing. Let's try it out.
Let's put this into practice with question 44. We've got a 6,000 Newton force applied to a smaller piston with an area of 0.40 square meters. The bigger lifting piston has an area of 0.90 square meters. So what's the output force? Just set up the ratio. 6,000 over 0.40 equals our unknown output force over 0.90. Solve that and look at the result. Our relatively small 6,000 Newton push is magically transformed into a massive 13,500 Newton force. That is definitely enough to lift a car.
Question 45 uses the exact same logic, but this time we're hunting for the area. A 720 Newton input force on a 0.20 square meter piston needs to lift 10,800 newtons. We set it up. 720 over 0.20 equals 10,800 over our mystery area 2. Cross-multiply, solve it out, and we find that the larger piston needs a minimum surface area of 3.0 square meters.
Cruising right along to question 48. We're looking at a heavy crane's hydraulic lift. It uses a 1,400 Newton force on a half square meter piston to lift 5,000 newtons. Once again, relying on Mabda Pascal, 1,400 divided by 0.5 equals 5,000 divided by our unknown output area. Do the math, 5,000 times 0.5 divided by 1,400, and we get a required area of exactly 1.79 square meters.
All right, let's bring it all home with our last two problems side by side. In question 49, an 11,000 Newton input on a 1.5 square meter piston drives an output piston of 2.25 square meters. Setting up our ratio, 11,000 over 1.5 equals output force over 2.25. That gives us a beefy 16,500 newtons of output force. And for our final challenge, question 51, a 1,100 Newton force is lifting a 15,000 Newton car using a 10 square meter platform. So 1,100 over our unknown input area equals 15,000 over 10. Crunch the numbers, and you'll find the smaller piston needs an area of just 0.73 square meters.
And just like that, we did it. We have reviewed and absolutely crushed every single question on this list. You have officially mastered forces, pressure calculations, buoyancy, and Pascal's formulas. You are totally, 100% ready to ace this physics exam.
But before I let you go, I want to leave you with one final thought. These aren't just abstract equations you bubble in on a test. This is literally the mathematical language of the physical world around us. By figuring out these exact rules, humanity was able to build submarines, giant cargo ships, and the massive hydraulic cranes that construct our cities. So when you ace this exam, and you will, how are you going to use these incredibly powerful physics principles to engineer the machines of our future? Thanks so much for hanging out with me in this explainer, and good luck out there.
Welcome back, everyone, to today's explainer. I'm thrilled to step into the role of your bilingual science teacher for the day. We've got an absolutely fantastic dual-topic lesson queued up for you. We're going to explore the invisible forces of fluid dynamics and physics, and then we'll pivot over to chemistry to break down the fundamental classification of matter. Whether you're here to master the core concepts or just want to pick up some bilingual scientific vocabulary along the way, you are exactly where you need to be. Let's get to it.
So, here's our lesson plan for today. First up, fluid dynamics theory. Second, real-world apps, so we can actually see these invisible forces at work. Third, classifying matter over in chemistry. And finally, a practice quiz review to lock all of this in.
Okay, let's dive into this. Section 1, Bernoullian viscosity, the physics of moving fluids.
We're kicking things off with two absolutely fundamental concepts. First is Bernoulli's principle, or Mabda Bernoulli. Bernoulli noticed a fascinating relationship. If you restrict the flow of a fluid, its velocity actually increases. And here is the absolute golden rule you need to remember. An increase in the velocity of a fluid stream results in a decrease in the fluid's pressure. I know, it sounds totally counterintuitive, right? But fast-moving fluids actually exert less pressure. Plus, fluids naturally want to move from areas of high pressure to areas of low pressure. That one simple rule literally drives massive events like global weather patterns and ocean currents. Then, looking at the second concept, we have viscosity, or alosage, which is just a fancy way of expressing a fluid's resistance to flowing. Just think of the difference between pouring a glass of water versus pouring a jar of thick honey. That's viscosity in action.
Moving right along to Section 2, real-world fluid applications, fluids in action. Let's take these invisible physics rules and see how they power things you use all the time.
And a standard paint spray gun brilliantly illustrates this concept in action. Here's how it works. First, compressed air moves at a super high speed through the horizontal hose. Based on Bernoulli's principle, that high-speed air creates a low-pressure area right at the top of the vertical tube that sits down in the paint. And since we know fluids move from high to low pressure, suction basically draws the paint upward from the higher pressure inside the bottle right up to that lower pressure area at the top. Finally, that fast-moving air thins the paint out, spraying it out of the nozzle. The whole shebang relies entirely on fast air creating low pressure.
Now take that exact same principle and scale it way, way up to fly massive airplanes. Airplane wings are specifically designed with a curved upper part and a flatter lower part. Because of that curve, air literally has to move faster over the top of the wing. Just like with the spray gun, greater speed reduces the air pressure above the wing. Meanwhile, the slower air moving under that flat bottom maintains a much higher pressure. Since air pushes from high pressure toward low pressure, the air below the wing pushes upward, creating that net upward force we call lift. It's like magic, but it's just physics.
You don't even have to look up at the sky to see this happening. You can literally just look in your closet. Inside a vacuum cleaner, there's a rotating fan. As it spins, it forces air out through the exhaust port. By constantly pushing air out, the fan creates a lower pressure area inside the machine. So, what does nature do? It tries to balance things out. The high-pressure air outside the vacuum rushes into that low-pressure zone, carrying all the dirt and dust from your carpet right through the suction inlet.
Excellent work on the physics portion. Let's gracefully shift gears to chemistry for Section 3, Elements and Compounds, Classifying Matter.
We're moving from the physics of macroscopic motion down to the microscopic building blocks of the universe, starting with the absolute purest form of matter, the element, or Unsur. An element is a pure substance made of only one type of atom. You literally cannot break an element down into other elements by any physical or chemical means. It's as basic as it gets. Whether those atoms exist individually like helium or in pairs like a diatomic oxygen molecule, it is still just one type of atom. To date, there are 118 known elements, and out of those, 92 occur naturally in our universe, while the rest are man-made.
Let's put this into perspective with 4 specific elements and their everyday applications. First up, silicon, element 14. We find it in sand, and it's the absolute crucial component for making the computer chips running the device you're using right now. Next is magnesium, element 12, which is found in chlorophyll. Manufacturers actually use it in jet engines because it's incredibly lightweight, super strong, and resistant to corrosion. Then we have lead, element 82, famous for its intense density. That density is exactly why it's used in those heavy lead aprons that block X-rays from reaching your body at the dentist. And finally, aluminum, element 13. Like magnesium, it's a lightweight, strong, corrosion-resistant metal, and we use it in everything from jet airplanes to your kitchen frying pans and the soda cans in your fridge.
Now, what's really interesting about this next part is what happens when those pure elements actually combine. A compound, or murakkab, is a pure substance consisting of 2 or more different elements that are chemically bonded in fixed proportions. Unlike elements, you can break compounds down by chemical means. But here's the real magic of chemistry. A compound has entirely different properties than the individual elements that make it up. Take standard table salt, or sodium chloride. Individually, sodium is a highly reactive metal, and chlorine is literally a toxic gas. But chemically bonded in a fixed ratio, they create the delicious salt you sprinkle on your food. Water, benzene, carbon dioxide, they're all compounds.
Let's see how this builds in Section 4. Classifying mixtures, physical combinations.
So what happens when substances are combined physically, rather than being chemically bonded? You get a mixture, or makhlut. This is matter composed of 2 or more substances that can actually be separated by physical means. There are 2 main players here. First, the homogeneous mixture, or makhlut mutajanis, where components are evenly distributed throughout. If you dissolve salt in water, every single drop of that water tastes equally salty. Air and brass are also homogeneous. Then we have heterogeneous mixtures, or makhlut gair mutajanis, where the components remain completely distinct and vary throughout. Think of a salad, trail mix, or oil and vinegar. You can clearly see and easily pick out the individual tomatoes or pieces of lettuce.
Now, within those heterogeneous mixtures, we have 2 special categories, depending on how the particles behave. A colloid, or garawi, is a heterogeneous mixture with particles that never settle. That liquid paint we talked about earlier in the spray gun, that's a colloid. The particles remain suspended forever. Fog is another great example. It's liquid suspended in gas. A suspension, or muallaq, on the other hand, contains solid particles that will eventually settle down to the bottom over time. Muddy river water or orange juice with a lot of pulp are perfect examples. If you just let them sit there, the heavy particles sink right to the bottom.
Congratulations! You have officially mastered the theory. Now it's time for Section 5, Practice Quiz Review. Test your knowledge.
Let's simulate a live review session and tackle our practice quiz, questions 52 through 60, starting with 52. What happens to pressure when velocity increases? Think about a fluid entering a narrow pipe. Its velocity becomes very high. So the crucial point here is applying Bernoulli's principle. As velocity goes up, pressure goes down. Easy. The correct answer is C. It decreases.
Moving right along to 53. What causes a low-pressure area in a spray gun? Remember our step-by-step breakdown from earlier? It is the compressed air moving at a high speed through the hose. High speed means high flow. Therefore, the logical deduction is answer C, high flow.
Question 54 asks, what fundamental relationship does Bernoulli's principle establish about fluids? We've hammered this a few times now because it is literally the anchor of this entire physics unit. The relationship is that increasing the velocity of a fluid stream results in a decrease in its pressure. So that makes the correct answer B.
Let's tackle 55 and 56 together. Question 55. Fluids systematically move between regions of differing pressures. What's the direction of this movement? Well, nature always seeks balance, so fluids are pushed from areas of high pressure to areas of low pressure. That's answer B. Now, sliding right into question 56. How do airplane wings manipulate air pressure to generate lift? Think back to how the wing is shaped. The upper wing is curved, which forces air to move faster over the top, dropping the air pressure there. The high pressure below then pushes up. That perfectly matches answer B.
Okay, rapid fire time for 57, 58, and 59. Question 57. Which term expresses a fluid's resistance to flowing? That's the textbook definition of viscosity. Answer D. Question 58. Inside a vacuum cleaner, how does forcing air out generate suction? It creates a low-pressure area inside which automatically draws the high-pressure air from the outside in. That's answer B. And question 59. What happens when fluid flow is restricted? Just like water being forced through a narrower pipe, restricting the flow forces the fluid to speed up, so velocity increases, which brings us to answer A.
And we're wrapping up our quiz block with question 60, what did Bernoulli actually discover? This firmly cements the absolute most important takeaway of our physics lesson today. He discovered that pressure decreases with velocity. The correct answer is B.
I want to leave you with this final thought. Science is the invisible force lifting planes and the elements in the device you're holding right now. My hope is that after this explainer, you walk away looking at the world just a little bit differently. I hope you see Bernoulli's fluid dynamics in every single gust of wind and the intricate chemical compounds in every object you touch today. So what invisible forces are shaping your world right now? Keep observing, keep questioning, and I'll catch you in the next lesson.
All right, let's jump right into this explainer. Today, we're decoding the mysteries of matter. We're going to unpack the fundamental chemistry of the world around us, looking at everything from pure elemental substances all the way up to really complex mixtures. Let's dive in. Here's our roadmap for today's session. We've got a pretty straightforward four-part plan. First, the classification of matter. Then, we'll explore different types of mixtures. After that, we'll tackle physical versus chemical properties. And finally, we'll look at the elegant methods chemists use to separate those mixtures.
All right, Section 1, the classification of matter.
It's honestly kind of mind-blowing how we can map out absolutely every piece of stuff in the universe with just one basic flowchart. Every single type of matter goes through this sort of sorting process. The main question you gotta ask yourself is, can it be physically separated? If the answer is no, boom, you've got a pure substance, or mononakia. Think of pure elements like gold, or compounds like pure water. But if you can physically separate it, like stirring sand into a glass of water, then you're looking at a mixture, a machlot. Keep this map in the back of your mind as we go.
Let's look at a real-world scenario from the text to ground this. Say you are building a jet engine. You need an element that is super lightweight, crazy strong, and totally rust-proof. Looking at the options, lead, silicon, magnesium, and helium, well, magnesium is obviously our clear aerospace winner here. And what makes an element like magnesium so special? Well, elements are the absolute bedrock building blocks of the universe. You literally cannot break them down into simpler substances by any physical or chemical trick in the book.
But here's where it gets really wild. When those unique elements bond together in fixed proportions, they form a compound. And the crazy part? The new compound usually has completely different properties than the ingredients that made it. Take sodium, a highly reactive metal that basically explodes in water, and bond it with chlorine, which is literally a toxic green gas. You'd think combining those would be a total disaster, right? Actually, scratch that. They combine to make perfectly safe everyday table salt. Chemistry is just magic with really strict rules.
Moving right along to Section 2, exploring different mixtures.
So, shifting gears away from those intense chemical bonds, let's talk about things that are mixed together but not chemically locked in place. What is the fundamental difference between a mixture and a pure substance? Well, because the ingredients in a mixture aren't chemically bonded together, like our table salt was, you can still pull the original pieces apart using simple physical tricks. You know, things like magnets, filters, or just boiling them. Now, we've got some specific and honestly kind of tricky types of mixtures to look at. Let's start with colloids, or EOT. A colloid is a heterogeneous mixture, meaning it's not perfectly uniform at the microscopic level. The particles floating inside are bigger than what you'd find in a completely dissolved liquid, but smaller than big floating chunks. And here is the absolutely crucial takeaway. Those particles never, ever settle out. They just stubbornly float there, suspended forever.
You actually interact with these all the time. Think about liquid paint. Paint is an awesome example of a colloid because the colored pigment just stays floating in the liquid. It doesn't drop to the bottom of the can. Or think about morning fog. You've got tiny water droplets suspended in the air. They scatter light, which, by the way, is exactly why turning on your high beams in the fog completely blinds you, but they are so incredibly light that they never actually fall to the ground. Fog is a classic colloid.
Now compare colloids to suspensions, or mu'alikat. Imagine stirring a handful of sandy dirt into a glass of water. It gets all cloudy at first, sure, but give it an hour and all that dirt is just sitting in a pile at the bottom.
Or take a bottle of Italian salad dressing. You shake it up, it looks mixed, but 10 minutes later, the oil and vinegar have completely separated into distinct layers. Because the particles in these mixtures eventually separate and sink, we classify them as suspensions.
Here's a really fascinating medical application of this concept. When you draw fresh blood, it looks completely uniform, right? It looks like a perfect, homogeneous solution. But if medical personnel put that vial into a high-speed centrifuge, that extreme spinning force reveals the truth. The heavy red blood cells get packed down at the bottom, white blood cells hang out in the middle, and the clear yellow plasma sits right on top. Since it separates out into those very distinct parts, whole blood is actually a heterogeneous mixture.
Let's jump into Section 3, Physical versus Chemical Properties.
Now that we've mapped out what matter is actually made of, let's look at how it behaves. A physical property is a characteristic you can measure or observe without ever changing the fundamental identity of the material itself. You can check an object's size, look at its color, feel its texture, or calculate its density. You could even take an ice cube and melt it down into a puddle. Through all of that, the core identity hasn't changed one bit. H2O is still H2O, whether it's a solid block of ice or a glass of liquid water.
So the big rule to drill into your head here is the difference between a physical change, التغير الفيزيائي, means the underlying identity stays exactly the same, you just changed what it looks like. But a chemical change, التغير الكيميائي, completely rewrites the script. It literally produces brand new substances with totally new identities.
Because chemical changes happen way down at the microscopic level, we need a sort of detective toolkit to spot them happening in the real world. Keep an eye out for these clues. If you mix two things together and suddenly there's a rapid release of heat or light, that's a major clue. If it starts foaming or bubbling to release a gas, or you notice a distinct new smell or a dramatic, unexpected color shift, yeah, you're almost certainly watching a chemical change happen. You're watching a brand new substance being born. Let's put that toolkit to work. Think about flammability, the ability for a material to catch fire and burn. Is that physical or chemical? Well, burning literally turns a piece of wood into ash and gas, so that is absolutely a chemical property. Now, what about just crushing an empty aluminum soda can? The can is flattened, sure, but it's still 100% aluminum. The identity hasn't changed at all, so that is just a simple physical change.
You actually see this stuff happening in your kitchen every single day. If you mix two clear liquids and they instantly start bubbling and getting super hot, bam, reference the toolkit. That's a chemical change. A new substance is forming. And it's the exact same logic with baking. Melting butter in a pan, physical change. But mixing flour, sugar, and raw eggs and throwing that into the oven to bake a cake, you're using heat to trigger a massive chemical reaction. Think about it. You can never, ever unbake a cake to get those raw eggs back.
And that brings us to Section 4, Methods of Separating Mixtures.
To wrap things up, we're going to explore how chemists elegantly undo these mixtures. Imagine a practical, everyday dilemma. You're at the beach, and you accidentally drop an entire shaker of salt right into a bucket of dry beach sand. What a mess! How in the world do you separate tiny grains of salt from tiny grains of sand? If you tried picking them out by hand, it would literally take a lifetime. But by using physical separation techniques, it's actually incredibly easy.
Chemists have a whole playbook for this exact kind of problem. The trick is to find just one physical property that differs between your ingredients and exploit it. Filtration, or tarhish, uses particle size. Liquids pass through the filter, solids get trapped. Distillation, known as takdir, and evaporation both take advantage of differences in boiling points. And magnetic separation, well, that's exactly what it sounds like. Use a magnet to pull out the metal.
So back to our beach sand problem. Here's the sequence. Just add water to the bucket. The salt dissolves, but the sand doesn't. Pour that whole mess through a filter, the sand gets stuck, and the salty water passes right on through. Let the water evaporate, and you've perfectly separated them. Or what if you spilled a mix of iron filings and sulfur powder? Just wave a strong magnet over the pile. The iron flies right up to the magnet, leaving the sulfur behind. It's so elegant. Finally, let's talk about boiling points. Distillation is amazing because you heat a liquid mixture, catch the vapor that boils off first, and cool it back into a pure liquid in a separate flask. You get to keep everything. But here's a really brilliant question. Why can you evaporate salt water to get the salt back, but you can't just boil pure water to get hydrogen and oxygen gas? Well, because salt water is just physically mixed, but pure water, H2O, is chemically bonded. Boiling is just a physical change. It turns liquid water into steam, but it doesn't have the power to break those chemical bonds. And that is a wrap on today's explainer. We've categorized matter, differentiated tricky mixtures, spotted chemical changes, and separated the supposedly inseparable. Now that you've got this understanding, I want to leave you with a thought. The next time you're cooking in the kitchen or just looking around your garage, take a closer look. What everyday mixture are you going to view entirely differently now that you know the hidden chemistry holding it all together? Thanks so much for joining me to explore all this, and I'll catch you in the next explainer.
Welcome, everyone, to a brand new explainer. Ahlan wa sahlan. We are jumping right into a comprehensive science exam review today, covering chemistry, energy, and the environment. We've got a lot of ground to cover, so let's just get right to it. Here's our quick agenda for this session. First up, conservation of mass. Second, we're comparing fossil and renewable energy. Third, the 5 stages of electricity. Fourth, human population growth. And finally, we'll wrap up with environmental impacts. All right, Section 1, conservation of mass, or in Arabic, Kanun Hifd al-Kutla. So, what is this absolutely crucial law all about? Basically, it states that the mass of substances before a chemical change strictly equals the mass of the substances after the change.
يعني قانون حفظ الكتلة على أن كتلة المواد قبل التغير الكيميائي تساوي كتلة المواد بعد التغير.
To put it simply, in our universe, matter is never magically created out of thin air, and there is no way it's ever magically destroyed. It simply changes form. Think of it like a perfectly balanced scale. The reactants you start with, like hydrogen and oxygen, carry the exact same mass as the water you end up with. The scale doesn't tip even a fraction of a millimeter. Now, the really interesting part here is the idea of a closed system. Say you have a fire burning a pile of wood. If we were to trap all of that in a completely sealed, closed system, the total mass of the original wood and oxygen would perfectly equal the total mass of the ashes. Even the smoke and the escaped gases are mathematically accounted for. Okay, so we know the rule. Let's see how this conservation law actually applies when we need to calculate exact mass in exam questions 80, 81, and 82. Let's tackle question 80 first. It asks, if the total mass of reactants before an experiment in a completely sealed glass flask is exactly 25 grams, what will the total mass of the products be after the reaction concludes? Well, remember our perfectly balanced scale? Because the flask is completely sealed, meaning it's a closed system, that 25 grams stays exactly 25 grams. So the answer is B. Now, moving to question 81. We're making table salt by mixing chlorine and sodium. We start with 4.04 grams of chlorine plus an unknown amount of sodium, and together they yield exactly 6.62 grams of salt. To find that missing sodium, it's just simple math. Subtract 4.04 from our total of 6.62. Do that and you get exactly 2.58 grams, meaning the correct answer is D. Wrapping up the math here with question 82, where we are forming water. We've got 2.02 grams of hydrogen reacting with 16.00 grams of oxygen. Following the law of conservation of mass, we literally just add those two reactants together. 2.02 plus 16.00 yields perfectly 18.02 grams of water, so option A is our winner there. Moving right along to section 2, fossil fuels versus renewable energy. The fundamental difference between these two major energy families really just boils down to their rates of consumption versus replenishment. Fossil fuels, think coal, oil, and natural gas, are non-renewable. Why? Well, because we humans consume them far, far faster than nature can ever replace them. I mean, it literally takes millions of years to form fossil fuels under intense geological heat and pressure. On the flip side, we have renewable energy. These are resources like solar, wind, and hydroelectric power, and they are defined by the awesome fact that nature replenishes them faster than we can actually use them. So applying that to question 83, option B hits the nail on the head based on those definitions. It states, non-renewable resources are consumed faster than they can be replaced, whereas renewable resources are replenished faster than they are used. Spot on. All right, section 3, the 5 stages of electricity. Let's look at the high-level roadmap of how a physical piece of coal is transformed into the electricity that lights up your bedroom. It happens in 5 sequential stages. Stage 1 is combustion, Stage 2 is the steam stage, Stage 3 is the turbine, Stage 4 is the generator, and Stage 5 takes it all out to the power lines. Let's break that journey down. During the very first stage, combustion, the chemical potential energy that's stored tightly inside the coal is converted into thermal energy as it burns. Next, we hit the steam stage. where that intense thermal energy heats up water until it vaporizes into high-pressure steam. This steam then forces its way forward into the turbine stage, where the thermal energy is explicitly converted into mechanical energy as it violently spins these massive turbine blades. Then we reach the generator stage. Those spinning blades turn the generator, transforming that mechanical energy into our ultimate prize, electrical energy. Finally, that electricity flows out through the power lines to us. But, energy conversion is never perfect, not even close. Based on the efficiency metrics in the textbook, there are some pretty wild extremes across a power plant stages. The most efficient stage by far is the generator, running at an incredible 95% efficiency. That means very little energy is lost when converting from mechanical to electrical. But conversely, the combustion stage is the absolute least efficient, operating at only 60%. That means a massive 40% of the coal's original chemical potential energy is instantly lost simply through the act of burning it. Kind of crazy, right? Let's put that knowledge to the test. Question 84 asks, during the very first stage, the combustion stage, what specific energy transformation occurs? Think back to that burning coal. We are taking chemical potential energy and converting it into thermal energy. That makes option C the correct answer. Next, question 85 asks, which stage converts thermal energy into mechanical energy by using high-pressure steam to spin blades? While spinning blades is the total hallmark of the turbine stage, so the correct answer is C again. Keeping the momentum going, question 86 tests us on those efficiency metrics we just talked about. According to the textbook, which stage loses the least percentage of energy, meaning which is the most efficient? We just saw that the generator stage totally tops the chart at 95% efficiency, making option B the correct choice. Finally, question 87. What type of energy conversion takes place inside that highly efficient generator? It takes the mechanical energy from the spinning turbine blades and converts it into electrical current, so option B is our correct answer here too. Shifting gears a bit, Section 4, Human Population Growth. To give you some perspective, back in the year 1700, the global human population was around 600 million. It took over a whole century until 1810 to hit 1 billion. But then, the curve just steepens wildly. By 1960, we hit 3 billion. Just 50 years later, in 2010, that number more than doubled to 6.8 billion. And the textbook data projects that by 2050, we are going to reach an estimated 9.2 billion people. That is a staggeringly rapid acceleration of human population growth. Which naturally leads us right into Section 5, Environmental Impacts and Pollution. As populations increase at that massive scale, we see some major objective impacts on the planet. First, deforestation, which leads directly to severe habitat loss. Then there's agriculture. While obviously absolutely necessary to feed everyone, certain farming practices strip the earth of plant roots, driving massive topsoil erosion. We also see urban development causing localized flooding simply because paved roads can't absorb rainwater. And finally, we see huge spikes in water and air pollution alongside the production of highly dangerous hazardous waste. Keep these specific impacts fresh in your mind for our final stretch of questions. Question 91 asks for the scientific term describing the total number of individuals of a particular species living within a given geographic area. That is the exact word-for-word textbook definition of a population, making option C correct. Moving right to question 92, what is a direct environmental consequence of agriculture? If we refer back to the textbook's warnings, farming practices, specifically tilling the soil, remove crucial plant roots. And without those roots holding things together, we lose several centimeters of topsoil every single year through erosion. Therefore, option B perfectly captures this direct consequence. What's really fascinating here is the direct connection between human construction and the water cycle. Take question 93 regarding large-scale deforestation. The source material tells us that cutting down trees actually decreases the amount of water evaporating from tree leaves, which results in less regional rainfall overall. That's option C. Then, think about question 94. Why do paved roads increase the risk of flood damage? It's pretty straightforward. Paved surfaces just cannot absorb water as quickly as natural land can. The water just sits there, pools up, and has nowhere to go. So, option B is our clear answer. Now, when we talk about pollution, there's a big focus on hazardous waste. Question 95 asks exactly how the document defines it. The source explicitly states that hazardous waste is material that can cause diseases to living organisms or can catch fire easily. Looking at our choices, option C provides that exact definition almost word for word. Let's bring it home with these final 3 questions. Question 96 asks for 4 major sources of water pollution. The textbook identified industrial runoff, human waste, agriculture, and construction sites or mines. That matches option C perfectly. For question 97, besides regulating the water cycle, why are all forest plants considered globally important? Well, because they are fundamentally responsible for absorbing carbon dioxide gas from our atmosphere. That makes option B correct. And finally, question 98, what specific hazard is associated with hazardous waste? As we just learned, it can easily catch fire or cause severe diseases, meaning option A is our final answer. As we wrap up this explainer, I want to leave you with a final thought to chew on. With our population rocketing towards 9.2 billion people, how will your generation engineer new, highly efficient solutions to balance our rapidly growing energy demands with the essential preservation of our planet?